climate change, and scientific uncertainty. So far in this course, I have presented a picture of Earth's changing climate that is familiar to those who follow the popular representations of climate change on mainstream and social media. Today we will peer behind such representations and try to understand what exactly climate change teaches us. To do that, we need to learn about some basic concepts relevant to climate science and draw some conceptual distinctions. The first important distinction we need to draw is between measurement and forecast. Measurement is any observation that determines within a defined margin of error a quantifiable empirical property. Here's an example, using a thermometer to determine that the temperature at the North Pole right now is 0 degrees Celsius plus or minus 1. That plus or minus 1 is the margin of error of the measurement. Typically, this means that the probability of the actual temperature being 1 degree of 0 degrees is 95%. Here's not an example of a measurement. Using your hand, determining that the bath water is hot. This is not a measurement for two reasons. First, hot is not an objective determination of a quantity. It is a subjective and qualitative determination. Second, there is no margin of error. Here's another example that is not a measurement. Scientists predicting that by year 2100, average global temperature will increase by 2 degrees Celsius plus or minus 1. This is objective and quantitative, and it comes with a well-defined margin of error. So, why isn't it a measurement? It is not a measurement because it is not an observation. It is instead a forecast. A forecast is any prediction within a defined margin of error of what a future value of a quantifiable empirical property will be based on previous measurements, theoretical calculations, or simulated models. So the previous example is an example of a forecast. As you can see, there is a 1 degree margin of error here. Again, it means the actual warming is predicted to be within 1 to 3 degrees Celsius within a 95% probability. Another important distinction is the one between detection and attribution. Detection is a form of measurement where a change or trend in an empirical quantity is found to be present. This is an example of detection. Scientists detected that the North Pole ice cap has shrank in the last 30 years. Importantly, detection doesn't entail anything about what caused the change or trend that is detected. That's the role an attribution plays. An attribution is a claim that a detected change or trend is causally linked to something else. For instance, the increased frequency and intensity of heat waves can be attributed to greenhouse effect. Very rarely, a trend or change can be attributed to only one factor. Usually, attributions are partial. For instance, the increased frequency and intensity of wildfires are partly attributed to global warming and partly to other factors. One last distinction which concerns likelihood, confidence, and statistical significance. Likelihood is the probability of a statement, a claim, or a hypothesis being true. Likelihood ranges between 0% and 100%. More common in scientific publications, likelihood is reported as a real number ranging from 0 to 1. For instance, the likelihood that daily temperature extremes have increased partly due to anthropogenic global warming is at least 0.95 or 95%. Some scientific reports about climate change use a descriptive scale of likelihood. Here's what those descriptions mean in terms of probability ranges. The probability in my example, for instance, would be very likely. We shouldn't confuse likelihood with confidence, which is the scientific community's degree of belief with regards to a statement. Confidence is a function of the degree of agreement between scientists and the status of the available evidence. Degree of agreement is easy to grasp. If almost all scientists agree about something, there is high agreement. If there is a majority who agree but there is still a sizable minority who disagree, it's medium agreement. And if there is no majority opinion, the situation is characterized as low agreement. The status of the available evidence is a bit more complicated. Here, the type, amount, quality, and consistency of evidence all factor in. For instance, if there's plenty of different sources of evidence that are all consistently indicating that 60 million years ago the Earth was 10 degrees warmer, scientists call that robust evidence. If, let's say, the only source of evidence is a computer simulation based on questionable parameters, then the evidence is characterized as limited evidence. Again, in some scientific reports about climate change, we encounter descriptions of the level of confidence. And this table tells you what those descriptions refer to. Finally, there's statistical significance, which is a measure of how likely we are to detect a change or trend, given that the detected change or trend is not real. Consider, for example, the statement, Earth has warmed up about 1 degree Celsius in the last 100 years. Here, the inequality in parentheses is called the p-value. The p-value tells us the likelihood of detecting something if what we are detecting isn't real. Since the p-value is less than 0.05, the probability of scientists detecting a 1 degree warming is less than 5% if that warming has actually not happened. When the p-value is less than 0.05, like it is here, the statement the p-value is associated with is called statistically significant. Now let me ask you a question which I don't expect you to answer correctly, unless you are well proficient in statistics. Assuming that the statement in the example is true, what is the likelihood that Earth has actually warmed about 1 degree in the last 100 years? If you said 95%, then you are wrong. You are wrong, but you are not alone. Most people make this mistake. They say, well, the p-value tells me that the likelihood of getting it wrong is 5%, so the likelihood of getting it right must be 95%. But that's sloppy reasoning. The p-value doesn't tell you the likelihood of getting it wrong. It tells you something very specific. The likelihood of detecting a 1 degree increase if there isn't one. You can't infer anything from that alone about the likelihood of there being a real 1 degree increase if we detected a 1 degree increase. That's probably too abstract, so let me make it a bit more relatable. Imagine that for some reason you are walking through a cemetery at night. You are not a superstitious person, but understandably you are still a little bit nervous. Suddenly, you catch something that looks like a ghost in the corner of your eye. Suppose that your eyesight is good, but then again, the cemetery is dark, and you are nervous, and you aren't infallible. So you estimate that the probability of seeing a ghost is 5% if there is no ghost. Should you then conclude that, therefore, the probability of there being an actual ghost there is 95%? Of course not, because your prior knowledge makes you almost certain that there is no such thing as a ghost. Therefore, you cannot infer that there is almost certainly a ghost from the fact that your eyes detected a ghost. The odds of a visual or cognitive illusion are overwhelmingly high. What's the right answer then? In the global warming case, the right answer is complicated because unlike the ghost story, we don't believe that there is no such thing as climate change. Indeed, what we know from physics tells us that warming due to the greenhouse effect is very likely. But how much of a warming is likely in what time frame? That depends on the details. There's a lesson to remember, however. Statistical significance doesn't always entail a high likelihood. Many scientific publications are full of statistically significant results which are more likely to be false than true. In case you are curious, I'm linking a few articles on the subject in the video description. With that crash course in philosophy of science behind us, let's look at the available evidence in climate change with regards to natural disasters. The kind of evidence I will focus on in this section is based on measurements. We will discuss forecasts in the next section. Here there are two important questions. Are the frequency and intensity of natural disasters increasing? Which ones? And how much? And how much of that increase is attributable to global warming? The first question is a matter of detection, whereas the second question is a matter of attribution. In discussing these questions, I will focus mostly on reports by the Intergovernmental Panel on Climate Change, just like Roger Pielke does, and review the status of claims we encounter in mainstream and social media about the relationship between anthropogenic climate change and these disasters. Let's start with heat waves and heavy precipitation. In mainstream and social media, it's often stated that these events have already intensified due to the greenhouse effect. Let's see what scientists think. IPCC's fifth and most recent report states that the frequency of heat waves and warm spells has increased relative to the mid-20th century. There is medium confidence for this detection. And with high confidence, the report partly attributes the change to anthropogenic effects. Similarly, the frequency of heavy precipitation events have been detected to increase. Again, the level of confidence is medium. And with medium confidence, the increase is attributable to human origins. Here, there is a temptation to jump from the well-supported claim that extreme heat events have become more common to the idea that we must be seeing a large rise in the ocean levels already. So very soon, we must start building huge walls to keep the ocean at bay. Or maybe it is even too late to save our cities. But that's not what the data show, at least so far. According to the National Oceanic and Atmospheric Administration, the ocean levels rose only about 10 inches in the last 100 years. That's not a lot. Why so little? There are a few reasons. First, most of the melting is happening in the Arctic, as the heating there is much more pronounced than the Antarctic. But 98% of the total glacier mass is in the Antarctic. So the kind of melting that causes ocean levels to rise is melting slowly. Don't get me wrong, there is some evidence for a modest amount of warming in the Antarctic region, but heat waves are extremely uncommon there, in contrast to the Arctic region. Another reason why the Antarctic is losing its ice relatively slowly is the increase in precipitation. Yes, the old ice is melting, but some of it is being replaced by new snow. It's hard to measure the exact balance, which reduces the accuracy and precision of the forecasts of future ocean level rise. But what about flooding? Don't we at least get more flooding due to increased heavy precipitation events? The answer so far is no. There is little evidence indicating that the magnitude or frequency of floods have increased globally in the last 70 years or so. Indeed, IPCC scientists warn against the assumption that flooding is an inevitable consequence of climate change. They argue, blaming climate change for flood losses makes flood losses a global issue that appears to be out of the control of regional or national institutions. The scientific community needs to emphasize that the problem of flood losses is mostly about what we do on or to the landscape, and that will be the case for decades to come. This is of course not the same as claiming that flood risk in certain places like New Orleans, Bangkok, and Chicago has nothing to do with climate change. Their point is more nuanced. We can and should take action to reduce flood losses by more effective long-term urban planning and infrastructure maintenance. What about hurricanes and tornadoes, though? As you might remember, in an earlier lecture I explained that these extreme weather events are fed by hot surface temperatures. If extreme heat is becoming more common, hurricanes and tornadoes must also be becoming more common, no? Again, the evidence doesn't support this. Both the frequency and intensity of hurricanes are within expected variability, with no upward trend. Of course, the economic damage caused by hurricanes is significantly up. When corrected for inflation, the hurricanes in the last 20 years have caused hundreds of times of economic damage in comparison to those from the earlier 20th century. But this is not due to an increase in the intensity or frequency of hurricanes that make landfall. The reason the damage is substantially more is twofold. First, the population who live near the coastlines increased substantially due to urbanization. What's more, real estate prices increased again substantially. As a result, a hurricane that would have caused X dollars in damage in, let's say, 1924 can easily cause 100 or 200 X dollars in the 2020s. So the hurricanes themselves have not been getting any worse, at least so far. Indeed, this is precisely what we see when we look at the normalized hurricane damage data, which factors out coastal population growth and real estate price inflation. Normalized tornado damage is the same way. Overall, it's actually slightly down, but when we exclude the outliers, there's no trend. Fine. What about droughts? Again, there is little evidence for any global increase relative to the mid-20th century. In some locations, however, there are increases which we can detect with medium confidence. In other places, the opposite seems to be happening. They are becoming more humid. So far, I have reviewed what has happened up to this point, which doesn't cohere too well with the sensationalist reporting we encounter in mainstream and social media. But trends or lack thereof can change. One impressive thing about science is its ability to make predictions of future events and foresee trend changes before they materialize. And climate scientists are not that different. They don't just report what they have observed so far, they are also trying to predict what will happen to Earth's climate in the future. But Earth's climate is a complex system, so the calculations that are necessary for making any prediction beyond a few weeks require the use of simulated computer models. So let's try to understand how these simulated models work. Obviously, these models are run on computers, which are significantly more powerful than anything consumers have access to. This is something necessitated by the sheer complexity of the system the models are simulating, an entire planet's climate. Like any software running on any computer, you can think of these models as a function that takes a set of inputs and produces an output. The desired output in the case of climate science is a forecast, such as how much the global temperatures will increase, or how much the sea level will rise, or how much snow will fall on Antarctica by year 2100. The input, on the other hand, can, and often does, come from different sources. One such source is data from past measurements. We have reliable records of atmospheric carbon dioxide concentrations, for instance, going back millions of years. In some cases, data comes not from measurements but from experiments such as those that help us understand the atmospheric half-life of certain greenhouse gases. There is, of course, also data and insights that come from theoretical models. For instance, we don't need to do any measurements to calculate how much extra heat will be radiated back to space if the atmosphere becomes 1 degree warmer uniformly. It's just a sophomore physics problem involving blackbody radiation. Finally, part of the input can be from prior simulations. For instance, in order to simulate the ocean level rise accurately and precisely, we need to know how much methane hydrate there is on the deeper parts of the ocean floors and how much of it will be released due to warming of the oceans. But oceans are vast and really, really deep. It is impossible to figure out the unknown quantities by measuring. So the scientist's approach to a problem like this would involve creating another simulation trying to determine and forecast that, and using its output as input for the simulation trying to forecast the ocean level rise. The first two kinds of data are sometimes referred to as hard data, as they involve a direct kind of empirical observation. The two on the bottom are sometimes lumped together as soft data, suggesting that they are less reliable than hard data. This suggestion, however, is an overgeneralization. In some cases, especially theoretical models can provide very reliable data. In any case, this is how a simulated model works, in a nutshell. Scientists create a computer program that will take the input data and spit out a forecast about the future state of Earth's climate. Pretty much all predictions you encounter, from ocean level rises to grain production amounts, are produced in this way. The key question is this then: how reliable are simulated models? There are a few problems that limit their reliability. The first one is the discretization problem, which is the fact that continuous phenomena must be simulated in a discrete model, which leads to forecasting error. If that sounds too abstract, here's an illustration. Suppose that we are trying to simulate the movement of a billiard ball on a flat surface. The ball is so large relative to the atoms making it up that it might as well be made out of an infinite number of parts. But no matter how powerful your computer is, you cannot simulate an infinite number of parts. So a billiard ball will have to be simulated as a collection of a finite number of parts, either cubes or polygons, cumulatively approximating a sphere. What's more, these cubes or polygons will have to be much larger than individual atoms, because if we try to simulate each individual atom, our computational power will again fall significantly short. So we would have to make some approximations. But that's not the end of the discretization problem. We are just getting started. Remember, we are trying to simulate the movement of a ball? Movement involves two things: space and time, both of which are again continuous and infinitely divisible. But we can't simulate an infinite spatial and temporal resolution. What we can do is chop space into small blocks and time into thin slices and pretend that the ball is moving through these blocks and slices. If there's a force acting on the ball, for instance, we assume that the force has to remain constant until the ball shifts from one block or one slice of space-time to the next one, even though in reality the force could vary as the ball travels. All of this, of course, will lead to error. Remember, however, a climate simulation isn't simulating a billiard ball, a very simple and almost uniform object. It is simulating the climate of an entire planet. So the discretization error involved in climate simulations is much more serious than the garden variety. But it gets worse. All kinds of error compound. That is to say, the longer the forecast time frame is, the more error we end up with. And this is not limited to just the compounding of discretization error. Remember those data sets the simulation uses as input? They all have a margin of error, don't they? And that's why even the easiest things to predict, such as global temperature increases, pose extreme levels of uncertainty when we try to forecast beyond a few decades, which explains why these graphs look like a weird peeled banana. And it is relatively easy to forecast global temperature increases, where the biggest share of error comes from economic models about human behavior. Atmospheric and oceanic phenomena are chaotic. Small perturbations can lead to great and inherently unpredictable differences in the long run. In other words, good luck with forecasting anything like the precipitation patterns in a specific location, which are essential for knowing things like whether we will be able to produce enough food to feed the world population by year 2100. But sometimes people reject these concerns as irrelevant and ask, what about when climate models agree? For example, they all agree that global warming is a great threat and we have to stop it. What about that? We can formulate the sentiment behind this question as an argument, which is what Wendy Parker's essay, When Climate Models Agree, is trying to respond to. Here's how the argument goes. Simulated climate models agree that global warming will cause great economic and environmental damage. When climate models agree on something, we should believe it, or at least act as if it were true. Therefore, we need to believe that or act as if global warming will cause great economic and environmental damage. There are a few ways one can criticize this argument. The first one is by denying that simulated models agree. This criticism is somewhat promising because it is rare that climate models agree about the long run. And even if they were to agree about what will happen in the long run if we don't act, it is highly unlikely for them to also agree about what action would be effective. However, that's not Parker's criticism. Instead, she attacks the second premise and denies that when climate models agree on something, we should believe it or act as if it were true. According to Parker, agreement might be an artifact of reliance on the same low-quality data sources, sociological factors, and technical constraints such as discretization and non-linearity. Let's explore this a bit, starting with the technical constraints. From a computational perspective, non-linearity and discretization problems are just optimization problems. And optimization by its nature leads to convergence of solutions. So simulated models tend to look alike, not necessarily because of some fact about Earth's climate, but perhaps because there is one optimal way of representing a billiard ball using 1,000 polygons. But there might be more to it than just efficient coding. Sometimes people agree with each other because they are getting information from the same source or because there are social pressures pushing them towards agreement. Let me give you an illustration of this from my own youth. I used to go to a high school near train tracks, but the tracks were not directly visible from the school. To see them, you had to go over a hill. One day, I decided to do a social experiment. I told the guy sitting next to me in class that I was walking near the tracks during my lunch break and I saw a train hitting a cow. Of course, I was lying, but he believed me. Next day, everyone was talking about the train and the cow. And they were convinced, or they were acting as if they were convinced. I didn't want to expose anyone's gullibility any more than I wanted to publicize my own dishonesty, so I kept the truth quiet. But I learned one important lesson that day. Falsehoods and errors tend to multiply, and people desire to fit in by repeating what they hear. Especially in an environment like a high school, if anyone has any serious doubt about what others say, they tend to keep it to themselves. And climate scientists are also human. Here, I'm not blaming any of them of consciously repeating a false forecast as if it were true, but there are significant professional pressures acting on scientists, perhaps similar to the social pressures acting on a high school kid. To keep their jobs, to get promoted, or to get funding, they need to get publishable results. Studies show that outliers are harder to publish. So whenever there is freedom to choose ranges for a variable among the input, scientists will likely choose a range that will make their forecast cohere with what is already in the literature. In other words, the logic of simulation-based forecasting and the sociological realities of science might be encouraging selective reliance on meager, low-quality, and contradicted evidence. And simulation forecasting is essentially a garbage-in, garbage-out business. If your input is low quality, your output cannot be high quality. It's important to not misunderstand the implications of all of this, however. Neither Parker's nor my goal is to debunk climate science or simulated climate models. We are both trying to give our audiences a more realistic picture of the reliability of the forecasts sensationalist mainstream and social media presents as if highly reliable. When you read reports such as IPCC, you in fact realize that climate scientists such as Roger Pielke are much more measured in their level of confidence in any particular forecast, even when it is in agreement with other forecasts. And now I hope you understand why this is so. Another caveat is that we might not need the argument from agreement between simulated models after all, because we could always fall back to the precautionary principle to advocate for action against climate change. What do you think? Is Parker being fair to simulated models? Can the precautionary principle motivate collective action in the absence of reliable agreement? This brings me to the end of this lecture. Send me a message if you have any questions. Thank you for your patience, and I'll catch you next time.